Hi everyone, welcome back to our channel. Today we are going to discuss about the basic Kirchhoffs laws used in circuits and network subject. So if you understand these laws, you will be very professional in solving all the problems of circuits and networks. So let's try to discuss what is the importance of these KCL laws. Basically, these KCL laws and KVL law is designed for easier analysis of an electrical network. Already in the previous class, we can already discussed an electrical circuit means which consists of a closed path with the help of an active elements and passive elements. So you can see here this battery is an active element, this resistor inductor is a passive element which forms a closed path. This is called as an electric circuit which has a single closed path. And if you have a one more inductor and a capacitor, this also forms an another closed path. This is also called as a single closed path, where we can call it as an electrical circuit 2. This is circuit 1, circuit 2, more than one closed path or more than one circuit. Therefore this is called as an electrical network. So more than one circuit means it may be two electrical circuits, three, or it may be four, or up to infinity. If more than one closed path is there, then it is called as an electrical network. So our laws are used for easier analysis of our electric circuit, which consists of a battery, resistor, inductor, and capacitor as the energy absorbing elements, where these elements are called as passive elements. Okay, so an electrical network is formed with the combination of resistor, inductor, capacitor with an active elements as battery or generator. So there is the main purpose of Kirchhoff laws. This is used for easier analysis of an electrical circuit and network. So here we have two kinds of laws. One is KCL as well as KVL. So KCL, the name itself, Kirchhoff's current law, it deals with the direction of flow of current. And one more law is there. This deals with the voltage source and voltage drop in a closed path. Now let us try to discuss about Kirchhoff's current law. Kirchhoff's current law states is algebraic sum of currents at a node is 0. This is the first statement. The second statement is the algebraic sum of entering currents to a node is equal to the algebraic sum of leaving currents at a node. Let's try to analyze this definition. So I'm considering a node. This is nothing but node 1. So here the current I1 is entering, current I2 is entering. The leaving currents are I3, I4, I5. Now let us try to apply our Kirchhoff's current law. Apply KVL at the node 1. What are the entering currents? I1 current is entering and I2 current is entering. Okay. And what are the leaving currents? I3 current is leaving, as well as I4 current is leaving, as well as I5 current is also leaving. So what is value of I1 is 1 ampere, I2 is 2 ampere, I3 is 1 ampere, I4 is 1 ampere, I5 is 1 ampere. So 1 plus 2 is 3 amperes. 3 amperes is equal to 3 amperes. So that's what the meaning of KCL. The algebraic sum of entering currents is equal to algebraic sum of leaving currents, where I1, I2 are the algebraic sum of entering currents. You can see here algebraic sum. This plus symbol is called sum. It's called algebraic sum is equal to the algebraic sum of leaving currents. Leaving currents are I3, I4 as well as I5. The entering currents are I1 and I2. This can also be written in one more form mathematically as I1 plus I2 minus I3 minus I4 minus I5 is equal to 0, which states that the algebraic sum of currents at a node of a circuit is 0. You can see here this is 1 plus 2 minus 1 minus 1 minus 1, which is plus 3 minus 3, that is equal to 0. So this is the definition of the algebraic sum of currents at a node. So the algebraic sum of currents at this node is equal to 0. This is what a KCL states. This can also be stated as the algebraic sum of entering currents is equal to the algebraic sum of leaving currents. So that's why these Kirchhoff laws will help us for easily solving and given complex electrical network. So already I told network means more than a single closed path. This is single closed, I mean an electrical circuit one, and this is an electrical circuit two. More than one electrical circuit is there. That's why this is called as an electrical network. Now, similarly, let us try to solve some problems on KCL and KVL. So, let's try to understand what is meant by Kirchhoff's voltage law. So, the expansion of KVL is Kirchhoff's voltage law. So, what this states is, so this is like the algebraic sum of voltage source or voltage drops. The algebraic sum of voltage source and voltage drops in a closed path is 0. Okay, or you can write down the voltage sources is equal to voltage drop. So you can write down in two forms. This is first form, this is second form. Let us try to analyze with an network. So I'm considering this is a battery 1, this is a battery 2, and this battery is connected to an resistor 1, and it is connected to one more resistor. So the terminals of the battery are already marked in the problem. This is V1, this is V2, this is nothing but R1, this is nothing but R2. So I am assuming a current of I amperes is flowing whenever the current is entering. This is plus, this is minus. So current I flows here, this is positive, this is negative. So here you can see here. Now let's try to write down the KVL equation. Just apply Kirchhoff's voltage law inside the loop. So voltage law means we have to write down V is equal to I into R. It should be only a form of voltage. So here the current is, so current is traveling like this, I amperes. Current is leaving. I am assuming writing the KVL with respect to leaving terminals. Why? Because the analysis is very easier with respect to leaving terminals. So current is leaving. What is the polarity of V1? Which is nothing but plus V1. So current is leaving. What is the polarity of another voltage source? Which is plus V2. And current is entering the resistor and is leaving. So what is the total voltage across the resistor? This is current is leaving. What is the polarity of this source? Minus I into, what is the resistance at this point, which is R1. It's nothing but minus R1. Again current I is flowing like this. What is the leaving terminal? Which is minus. And what is the drop created by this resistor? A current of I amperes is flowing, offering a resistance of R2, that is equal to 0. So now you can see here our statement of KVL is verified. The algebraic sum, this is nothing but V1 plus V2 minus and minus. It's nothing but plus into minus indirectly. This is also plus into minus. Plus into minus is also minus. Plus into minus is also minus. Both are same. So since the definition I'm explaining is the algebraic sum, V1 plus V2 plus drop IR1 plus IR2 is called algebraic sum of voltage source, where V1, V2 are called voltage source, IR1, IR2 are called as voltage drops. The algebraic sum of voltage sources and voltage drops in a closed path is equal to 0. This is how we want to understand. This can also be written as, so shift this negative terms to the right hand side. V1 plus V2 is equal to I into R1 plus I into R2. So now the second definition follows is voltage sources is equal to voltage drop in a closed path. What are the voltage sources? V1 and V2 are the voltage source. What are the drops? IR1, IR2 are the voltage drops. V1 and V2 are the voltage source. You can see here both are same. Just for your convenience, it is explained as the algebraic sum of voltage source and voltage drops in a closed path is 0, or voltage source is equal to voltage drops in an closed path. This is all about Kirchhoff's voltage law. So hope you understood the basics of a Kirchhoff laws. So first, an electric circuit will be there. More than one electric circuit is called network. These laws are used for easier analysis of this kind of complicated networks. KCL deals with the flow of currents. KVL deals with the voltage across an resistor. So the algebraic sum of entering currents is equal to the algebraic sum of leaving currents is the definition of KCL. So similarly, the algebraic sum of voltage source and voltage drops in a closed path is equal to 0 is the definition of Kirchhoff's voltage law. We will proceed with the next two problems of different methods in KCL and KVL. Thank you for watching. If you are watching the channel for the first time, like the channel, share with your friends, and if you have any doubts, let me know in the comment section. I can answer your doubts. And this is a free channel for the development of students. Kindly subscribe the channel and support the channel for the development of students. Thank you for watching. Yours obediently.